All right, we're nearing the end of Unit 2.5 and talking about the periodic table. Today we're going to look at a lot of the trends within the groups of the periodic table. Some of these groups have names specifically to them. Some of them were talked about probably previous. If not, we'll definitely bring them up again and again and again. And also some of the trends that are in the periodic table within these groups, we'll remember to make note of why that is based on the three trends that we have talked about previously. So, metals. If you look on our periodic table, the majority of our periodic table is metals. And that's why, again, I like to call the transition metals the transition metals, because the majority of them are metals to begin with. Now, what are metals? Well, metals are good conductors of heat and electricity. That means they go out hot or zap zap. There's a reason why we have copper wires to transmit electricity, even though it's not the most efficient at transferring electricity. Silver technically is the best metal to transmit electricity. But because of certain chemical properties, we don't use silver. The next best one to transmit electricity is actually gold. But there's something else that's wrong with gold, and that's the ching ching, bling bling. And so therefore, we don't use gold very often, except in the space industry. In the space industry, we use gold a lot because gold will not corrode, and therefore it has that's a chemical property that it has, is that we will able to do that. Now, your Ethernet or phone cables, when you plug something into your phone into the not your phone to charge, but your phone cables, like the old ring phones, or your Ethernet cables, those usually have little small amounts of gold in them. Even your motherboard in your computers have inlaid gold imprinting, so allow that electricity and that information to pass quickly. Now, they also are bright and metallic in luster, meaning they're shiny and briny and pretty. Okay? They're malleable, meaning you're able to hammer them into sheets. Okay? That's why they're used for artistic purposes many times. It's why the Statue of Liberty is made of copper, because it could be hammered into sheets. Now, why is it green? That's because of another property of copper, and it was actually known that it was going to turn green. Okay? That was a property, because now it actually resists a lot of weathering because it has that green color to it. They're ductile, meaning you're able to be drawn into wire. Not drawing as in, drawing, but actually being pulled into wire and pressed into wire in that way. And so that is just a little bit different, but those are things that metals have. Again, the majority of the periodic table are metals. Now, they might not all conduct electricity and heat as well as one of the other. They might not all have a bright, shiny metallic luster compared to others. Obviously, there are a few that we would probably guess. Gold, silver, and copper, platinum are very shiny as well. Zinc can be very shiny, but some of these lose their shiny luster very quickly because of what's called oxidation, meaning their interaction with oxygen. Now, all of the metals are solids at room temperature with the exception of mercury. Mercury is one of two elements on the periodic table that are liquids. Mercury is the only metal that is a liquid. They have low ionization energies. Why do they have low ionization energies? Well, they have larger atomic radiuses. The larger your atomic radius is, the more likely you're going to lose an electron. And so therefore, metals form cations. Some of the more important compounds are metal oxides. Well, that's because oxygen is so abundant in our atmosphere. It's kind of a nice thing. Not the most abundant in the atmosphere. Nitrogen is the most abundant in the atmosphere at 78%. Oxygen is next at 21%, but nitrogen doesn't react the same way as oxygen does. Therefore, oxygen makes these things. And I talked about in the previous slide some of these metal oxides that are super duper important, as such as copper oxide. Copper oxide gives that green hue, that resistance to weathering or further oxidation or reactions. Makes it all, in a way, almost chemically inert. Now, lead oxides also have a look to them, probably as they are also abundant. Iron oxides are prevalent and abundant. Some of those find their way onto our car, and they're not ones that we, are saying are important compounds because, rust makes our cars not always look the best. And a lot of times people think that a rusting car is losing mass, but in all reality, a rusting car is gaining mass. It's a property of rust to be flaky, and that in turn is why it loses in kind of there. But if you were able to catch all of the rust that would fall off of a vehicle, the mass of the vehicle would actually increase. Most of the metal oxides are considered basic, meaning they form a basic solution having a pH greater than 7. Okay, so their bases, not like a thump base. They are base when you're looking at, like, is it an acid or is it a base type of thing. So that pH of greater than 7 is usually around the 8 to 12 or 14 range. Okay, so those are some of those. Some of them are other ones. There are a number of other metal oxides. I mean, silver oxide is very prevalent. Always remember having to go over to Grandma's house and polish the silver before a family gathering. Why? So that you would polish off that silver oxide, that oxidation that's occurring on it, so that the silverware looked nice. So maybe some of you had to do that too. I don't know. Nonmetals. They're a very small group, not the smallest group, but they're a very small group on the right-hand side of the periodic table. Nonmetals, they're not metals. They're poor conductors of heat and electricity. They're boring. They have a typical dull color. They are not malleable, meaning they cannot hammer them into sheets, and they are not ductile, meaning we cannot draw them into wire. Now, some of the nonmetals can be pressed into pellets. Sulfur, when it's in its powder form, can be pressed into a pellet. And the same thing with, say, phosphorus. It can be pressed into a pellet. They are not able to be hammered because they are very brittle. The noble gases, I'm going to hopefully guess that you would figure that, you can't press them very much considering that they're a gas. So that also probably has a little bit to do with it. When we look at which ones are actually solid, there are very few of them, because you have this whole group on the in group 18 that are a gas, fluorine, chlorine, oxygen, nitrogen, they're all gases, so it doesn't really leave a whole lot for being a solid. That doesn't mean that they can't chemically react with a metal to form a solid, but that's different. We're looking at just the elements as themselves by themselves. Now, this is a part for those that are in my classes. They need to know the 7 diatomic molecules. You need to know that it's hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are the 7 diatomic molecules. Meaning, when we find them in nature, they are in a pair with themselves. Now, of these nonmetals, bromine is the only other liquid on the periodic table. It's the only nonmetal liquid on the periodic table. Mercury is the only metal liquid on the periodic table. The noble gases, well, they're gases, and everything else is going to be a solid, which really isn't a whole lot. They form anions, which means they gain electrons because their atomic radius is smaller because they're way on the right-hand side of the periodic table. They're going to be smaller, which means they're going more likely to attract electrons. And therefore, that will allow them to fill their outer shell, giving them that electron configuration similar to that of a noble gas. It's easier for them. They're so close. So when nonmetals react with oxygen, such as like nitrogen or chlorine or bromine or iodine, another nonmetal, they tend to form what's called molecular compounds, and they tend to be acidic. Now, coming back to those diatomic molecules, how do we memorize them? How do we memorize those diatomics? Well, there's a number of different ways to memorize the diatomic molecules. You can just flat out memorize them. Or there have been a couple ways in which I have found that work for me. One of the ones that was taught to me by a student was saying H, NOF, and down. Because if we look at our periodic table, you would see H for hydrogen, NOF, and then down. So H, NOF, and down. Now I tend to have used that instead of using a swear. I'll say what the H, NOF, and down as instead of using swears. Another way that I thought of when I was in high school, sitting in a chemistry classroom as a junior many, many years ago, is that if you look at your periodic table, element number 7 is nitrogen. And if you draw a 7 starting at 7, you have 6 of the 7, and so you really only would have to measure that. Now, my periodic table when I was in high school had hydrogen written above fluorine. So you would just write a kind of a weird looking one, and so you would write that just a little bit different, so you just write it that 7 to include that hydrogen. That's what my periodic table had. they tend not to do that, and I like it because it kind of does confuse students, I think, on kind of where it's at. So if you draw a 7 starting at 7, that's going to get most of them. But H. Schnaufendown, after I heard that one, I enjoyed that one. So it's an important, that is something we are going to need to know kind of moving forward, not just in this unit, and it's really, really going to be important in the naming unit. So kind of in a way, after the unit 3, which is our naming unit, when we talk about oxygen, we're talking about O2. When we talk about chlorine, we talk about Cl2. Okay? They're always going to be in that pair. If we wanted to talk about elemental oxygen, we would very specifically say elemental oxygen or monoatomic oxygen. So to make sure that we're all on that same page, that's what we do, is say, when we're talking about this, it's going to be very specific. We will make sure that you know we're not talking about the diatomics. So kind of for the purpose of moving forward, when we talk about diatomics, when we say any of these diatomics, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, we're dealing with the diatomic. We will specify when we're not. So that's an important thing as we move forward, especially in chemical reactions. Now, the smallest group on the periodic table is the metalloids, or sometimes called as the semimetals. I've seen this group under debate on what is and what is not a metalloid or a semimetal. When I was in high school, aluminum was considered to be a metalloid or a semimetal. Now, it's considered to be just a metal. So things change. If you look on a periodic table, it is kind of a stair case that you might see. They have properties of both metals and nonmetals. Silicon looks very metallic when it's just elemental silicon. Very shiny, very metallic luster. However, it doesn't conduct electricity all that well, but it does conduct some. Antimony and germanium have lusters as well, but they don't tend to hang around very well. And some of these don't have very good, conduct heat very well because they melt at very low temperatures. And it is their property of that they do conduct electricity, but not a lot or very well, is why we would use them as semiconductors, especially for computers. That's why in the Silicon Valley, where a lot of the software area has really developed, is because of their proximity to actually very pure silicon dioxide or sand, that they're able to actually get very good yields of silicon, and so that they can make their computers as they need. Now, some of the groups on the periodic table have names themselves, and the one is the alkali metals. They are metallic and they are solids. They are not normally found by themselves in nature because of their ability to chemically react. The alkali metals, or group 1 metals, are soft, and when you can cut them with a butter knife. Now, the alkali metals are historically reactive in water. They're very reactive in water, and actually they have to be stored in mineral oil so that they don't chemically react with the water in the air. That is why it is under suggestion of a lot of the schools to not have group 1 metals housed in a high school because they might chemically react. Not all chemistry teachers live at the school. Some of them would never come in and check their mineral oil levels of their metals over the summer, which needs to happen. You would actually should check your oil levels once a month. And they can be very highly reactive. And you actually need a specific fire extinguisher to hold or to have the alkali metals in a facility as well. Now, obviously, that's what times are like now. When I was in high school, it was a kind of willy-nilly, go grab some sodium or potassium out of the stock room, which was a very small room, not good ventilation, and we grabbed it and then we played with our group 1 metals in the lab and did things that we weren't supposed to do. Because of those types of things and that loosey-goosey attitude is probably why we have the regulations that we do now. Weird how that works. So, as I stated before, they're not really found by themselves in nature. We actually have to react them to get them by themselves. And so they do this because they have such low ionization energy. Meaning because of their atomic radius is so big compared to the other ones, they lose those electrons so quickly. Now, by also losing those electrons at 1 electron so fast, they also form that noble gas configuration because they only have 1 electron to lose. So it's easy to lose it because it's hanging out in the outside and less visible because of shielding effects for that nucleus. And if we look at the chart here, we can see that the atomic radius goes up as we go down the periodic table. The ionization energy goes down, just like we said. The melting point and the density also have a connection, and they do have some similar properties. That the melting point actually goes down as you go down in the periodic table, and the density increases as you go down the periodic table. Now, there are sometimes those anomalies where you see sodium to potassium just a little bit different. And so those properties still there. There are properties, and I bet that you would guess that those same properties follow suit for some of these other ones as well. So here we have some demonstrations, and this is a video that we would show in class. I have it, I think, linked inside my YouTube channel as well. But let's put it inside the presentation so that we can see it.
Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group.
I think he meant more awesome.
Let's try cesium, our 5th alkali metal.